Hello, everybody. My name is Pratwal Hiramat from MTech Signal Processing and Communication. Uh, this presentation is about a highly influential paper titled Very Deep Convolutional Networks for Large-Scale Image Recognition, written by Karen Simonian and Andrew Zisserman from the University of Oxford. This paper was presented at the International Conference uh, on Learning Representation, that is ICLR, in 2015. In it, the authors propose a simple yet a powerful idea: building CNN, that is convolutional neural networks, that are very deep in terms of the number of layers, while keeping the structure of the network straightforward. Their architecture became known as VGGNet. That is what we're studying in the ongoing course, and went on to become one of the most widely used CNN models in the field of computer vision. This paper shows that increasing depth alone, without any fancy tricks, can significantly improve the performance of the model. So let us talk about the motivation of this paper. At the time this research was done, CNNs had already demonstrated their effectiveness in image recognition tasks, especially with the success of previous model, that is AlexNet, in 2012. However, many of these models used large convolutional filters such as 11 cross 11, 7 cross 7, and had relatively few layers. So the authors of this paper questioned whether depth itself could be a major factor in improving performance. Instead of using wide filters and complex architectural designs, they decided to keep the architecture consistent and simple, using only small 3 cross 3 filters throughout the entire neural network. Their main question was whether simply going deeper with the many small filters could lead to any better results compared to previous neural networks. And after the completion of this paper, the result is yes. The answer is yes. The main key contributions of this paper is a systematic study of the depth in CNNs. The authors constructed uh, and evaluated networks ranging from 11 layers to 19 layers, all built using small 3 cross 3 convolutional filters. They demonstrated that deeper networks could lead to better classification performance even when the overall design remains simple. Their approach achieved top results in the ImageNet large scale visual recognition challenge in 2014, where they secured first place in the localization track and second place in classification track. Moreover, the features learned by these networks were found to generalize well to other computer vision datasets, making them very effective for transfer learning. Overall, the paper highlighted the importance of depth in visual recognition models and set a new benchmark in CNN design. So let's talk about the architecture of this network. The architecture used in this network is very straightforward. The input to the network is a 224 by 224 pixel RGB image. The image is passed through a series of convolutional layers, each using 3 cross 3 filters with a stride of 1 and padding of 1 pixel, which preserves the spatial resolution. After some of these convolutional layers, the output is downsampled using max pooling layers that operate on 2 cross 2 windows with a stride of 2. Towards the end of the network, there are three fully connected layers. The first two have 4096 units each, and the final fully connected layer has 1000 units, corresponding to the 1000 classes in the ImageNet dataset. The final layer is a softmax, which converts the output into class probabilities. All convolutional and fully connected layers use ReLU activations. This entire architecture is simple and elegant, yet effective, highly effective. Uh, configurations, Adashi. In order to study the impact of network depth, the authors created 5 different configurations of the VGG network labeled A through E. These networks differ only in how many layers they have, with the overall structure and the use of small filters keeping it consistent. Configuration A has 11 weight layers, while configuration E has 19, making it the deepest model. The intermediate configurations B, C, and D have 13 and 16 layers. One of these, configuration C, also includes a few 1x1 convolution layers, which were added to increase nonlinearity without increasing the receptive field. All configurations follow the same pattern: convolutional layers followed by max pooling, and finally three fully connected layers. This controlled design allowed them to isolate the effect of increasing depth without introducing any other variables. So, why small filters are used in this neural network model? One of the central design choices in the paper is the exclusive use of the small convolutional 3x3 filters. The idea here is that stacking multiple small filters in sequence can approximate the effect of larger filter while offering several advantages. For example, 3x3 filters stacked together have the same receptive field as a single 7x7 filter. However, by stacking them, the network gains more nonlinear layers in between, which makes it more expressive and capable of learning complex features. Additionally, using three small filters requires fewer parameters than one large filter, which helps in reducing overfitting and computational cost. The design choice is a key reason why the authors were able to build very deep networks that were still efficient to train and generalize well. So now the training details uh, done used in these papers. The networks were trained using stochastic gradient descent with a momentum value of 0.9 and a batch size of 256 images. The learning rate was initially set to 0.01 and was reduced by a factor of 10 whenever the validation accuracy stopped improving. The authors used dropout regularization in the fully connected layers with a dropout rate of 0.5 to prevent overfitting, and also applied L2 regularization with a with weight decay factor of 0.5 into 10 to the power minus 4. To further improve generalization, the authors performed data augmentation by randomly cropping, flipping, and color shifting the images. For training the deeper networks, they used a clever technique where the first few layers were initialized using weights from a shallower, already trained network, and only the new layer were initialized randomly. This made training deeper models more stable and faster to converge. The testing procedure done by the authors. During testing, the networks were evaluated in a way that avoided the need for sampling multiple image crops, which had been common practice in earlier models like AlexNet. Instead, the fully connected layers were converted into convolutional layers, making the entire network fully convolutional. This allowed the network to slide over the entire image and produce class scores at multiple spatial locations. The final output was obtained by averaging these scores across the entire image. To improve robustness, predictions were also averaged across both original and horizontally flipped versions of the image. Additionally, the authors tested each model on multiple image scales to further improve performance. This method provided better accuracy and faster testing compared to the traditional multi-crop approach. So the classification results were classification experiments were conducted on the ImageNet 2012 dataset, which contains over a million images across 1,000 categories. The results showed a clear trend. As the depth of the network increased, the classification error decreased. For example, a 11-layer network had a top error rate of 10.4%, while the 19-layer network achieved 8%. In the predictions of two deep models, configuration D and E were combined, the error dropped even further to 6.8%. At the time, this was one of the best results in the world and significantly outperformed earlier models like AlexNet and even the more complex GoogleNet when using single model. This clearly demonstrated the benefits of going deeper into the network. Localization task done in this neural network model. In addition to classification, the authors also applied their network to the task of localization, which involves predicting the location of the object in the image in the form of bounding box. To do this, they modified the final layer of the network to output four values representing the center coordinates, width, and height of the bounding box. They experimented with two models, that is single class regression, where one model predicts bounding boxes for all the classes, and per class regression, where each class has its own bounding box prediction. The second method performed better, that is per class regression. They then combined the classification scores and the predicted boxes using a merging strategy. With this setup, their model achieved the best localization results in the ImageNet 2014 challenge, winning the localization track with an error rate of 25.3%. Transfer learning results. One of the most impressive aspects of VGGNet is how well it's learned features generalized to other dataset and tasks. The authors tested this by using the pre-trained VGG network as a feature of extractor for several standard data sets. Instead of retraining the entire network, they simply took the 4096 dimensional feature vector from the penultimate from the fully connected layer and used it to train a linear classifier. Even with this simple setup, the model achieved the state of a good result. For example, on the VOC dataset 2007, they achieved a precision of 89.3%. This shows that the VGG features are not just good for ImageNet; they are powerful and transferable across a wide range of visual recognition tasks. Conclusion. Uh, to summarize this, this paper demonstrated that simply increasing the depth of convolutional neural network while keeping the architecture simple and using small 3x3 filters leads to significant improvements in image classification accuracy. The authors showed that depth is a crucial factor in building a effective visual representation, and their models achieved a state good results at that time. The VGG networks became a new standard in the computer vision domain due to its simplicity, effectiveness, and versatility in using the network model. Then they later laid the groundwork for future developments in deep learning, influencing the design of even deeper models like ResNet, which built upon the side of increasing depth while keeping architectures manageable. Thank you.